Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. And this will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on using multifunctional amendments and site characterization to effectively manage back diffusion from a fractured sandstone aquifer. With that, I'd like to introduce our presenters for today. We are pleased to have with us Matt Burns, Technical Fellow and In Situ Remediation Practice Leader at WSP. Matt has more than 25 years of professional chemistry and engineering experience. He is based in Boston, Massachusetts, and brings chemical and microbial process and diagnostic expertise to assist local teams with challenging investigation and remediation projects in the United States and across the globe, including sites in Canada, India, Australia, Brazil, and several countries in Europe. He has authored numerous publications and conference platform presentations and is a frequent lecturer at continuing education workshops and webinars. We are also pleased to have with us today Maureen Dooley, Director of Strategic Projects at REGENESIS. Maureen has more than 25 years of experience in the remediation industry. In her current role at REGENESIS, she provides technical leadership for complex soil and groundwater remediation projects throughout North America, as well as remediation design, strategy, and business development in the northeastern United States and eastern Canada. All right, that concludes our introduction. So now I'll hand things over to Maureen to get us started.
Well, thank you, Dane. It's really my pleasure, and thank you, everyone. Good morning and good afternoon. As I say, I know how busy everyone is, so I truly do appreciate your time. But Matt and I are coming from Boston, Massachusetts, and very happy to be here today. Now, just speaking about Matt, I've known him for many years, and in regards to advanced diagnostics, Matt truly is a person who's a power user. He's applied these tools in an effective way for design, process optimization, and monitoring, and look forward to having him describe some of the ways he's applied these tools in his presentation today. The topic today is multifunctional amendments and site characterization to effectively manage back diffusion from a fractured sandstone aquifer. But before I turn it over to Matt, I want to just briefly describe the reagents that were used in this pilot program. As part of the presentation today, there are really two pilot tests that were performed. And for the initial pilot test, it was a biogeochemical pilot, and the reagents used for this particular test were 3D microemulsion, bioaugmentation culture BDI, and chemical reducing agent CRS. Now, just so you know, the 3DME is an electron donor, and that is applied as a dilute suspension. It has unique subsurface distribution characteristics. Now, the 3DME, in its molecular structure, it contains oleic acid and a polylactate, and this structure allows for an enhanced distribution, which is going to be critical for some of the testing that we present later today. And then once in the subsurface, the 3DME is going to have a controlled release of the organic acids into the aquifer, and that's going to in turn stimulate reductive dechlorination in the aquifer for about 2 to 3 years. Now, the CRS may be something you aren't quite as familiar with, but that's an iron-based solution that facilitates abiotic chemical reduction of the chlorinated solvents. CRS is pH neutral, and it's mixed with the 3DME. Now this is a soluble source of ferrous iron, and that's designed to precipitate as reduced iron sulfides, oxides, or hydroxides. And then these minerals are capable of facilitating, the abiotic degradation of the chlorinated solvents. And then the BDI is your consortia of your chlorinated solvent degrading bacteria. Now for the second pilot test, PlumeStop liquid activated carbon was applied with HRC and BDI. In this case, the hydrogen releasing compound is the electron donor, which is a polylactate, and again, along with the bioaugmentation culture BDI. Now, in getting started here, what is PlumeStop? Not everyone on the call may be familiar with it, so I just wanted to give you just a brief background. PlumeStop is a sorbent. So this is designed to rapidly remove contamination and promote degradation of the groundwater contaminants. Now the PlumeStop itself is activated carbon, and they're fine particles of about 1 to 2 micron. They're suspended in water through a polymer dispersion chemistry. Now the PlumeStop is going to behave like a colloid. It's going to bind to the aquifer matrix, and then in turn that's going to sorb the contaminants. The bacteria will colonize on the matrix of the PlumeStop itself, and thus was going to expedite the contaminant biodegradation. So in essence, what we're doing is we're painting the subsurface with this very, very thin layer of PlumeStop. So this is an important feature, and the ability to disperse and move the PlumeStop, or this liquid activated carbon, through the subsurface is really important. And just to be able to provide a visual, I just want to show this, and you can see that when you compare this to a powdered activated carbon, that's not going to move, but the liquid activated carbon is something that moves readily through the subsurface. Now, what are some of the problems that we're trying to resolve when we apply a material like PlumeStop? Well, one of the issues that we're often confronted with is really trying to remediate a site and achieve very low cleanup standards. One of the barriers to that quite often can be the idea of matrix diffusion or back diffusion. And what that means is quite often when we have a site, there's heterogeneity, and so you have high perm zones and low perm zones. And so contamination may be found in both of those areas. Now we inject a reagent and we can transmit that reagent through the high perm zones, reduce concentrations, but eventually you have this transfer from the low perm to the high perm, and that provides that rebound. So you may have multiple applications of reagents and still having a challenge in your ability to finally achieve that low standard. What PlumeStop can do is it can coat and manage at the interface of that low to high perm zone. And that's really one of the key components of this particular pilot test, and some of the information that Matt will be presenting is to be how can we manage these sorts of formations that have the potential for back diffusion or matrix diffusion. And so the other thing with PlumeStop is a platform. So this, you can support a variety of biologies or chemistries, aerobic, anaerobic degradation, different abiotic reactions. So quite often with PlumeStop, you may co-apply with different reagents to establish, again, the biology or chemistry that you're looking to support. But anyway, so let's get back to why you're really here, and that's to look at some options for a complex sandstone bedrock geology. Matt's going to present his approach to complex sites. He's going to discuss reagent delivery and placement, the ability to promote the desired reaction, and collect data to prove that these reactions are taking place. And finally, at the end of the day, I like to say we can have the coolest technology out there, but it needs to be economically feasible. So Matt is going to touch on that as well, and how some of these technologies may be appropriate for the site that he's looking into. So Matt, I'll turn it over to you.
Thank you, Maureen. As Dane mentioned, I work for WSP. I've worked here for the past 18 years, and that photo that you see of me over on the side there is a little bit dated. WSP is a multidisciplinary engineering firm with 36,000 employees globally. Here in the US, we have large buildings and transportation infrastructure businesses, and the environmental business is also strong and rapidly growing organically and through acquisition. During the presentation, I'll cover a couple of promising pilot scale tests at complex remediation site. I'll lay some groundwork for the pilot test discussion by describing my general approach to managing complex sites, and I'll try to leave some room at the end of the webinar for some questions. The signpost in the upper left corner of the slide will let you know where we are in the webinar. So if you need to duck out for a call, you'll know where we are when you come back in. Okay. I know intuitively that the site we'll be discussing today is a complex site, but complex site is a buzzword I've been hearing a lot the past few years, so I went looking around the internet to try to find a definition. Instead, I found a great survey in an IRTC presentation. In the survey, the respondents were asked what percentage of remediation sites are complex. More than half of the respondents, the yellow, brown, the darker blue, and the purple in the pie chart, these right here, thought less than 25% of all sites were complex. Another question asked about the respondents' experience with complex sites. About half had experience with 6 or more complex sites, and about half had been working on complex sites for more than 15 years. So apparently, one of the determining factors for a complex site is if it is a site that you are personally working on. There are many reasons why I think the site we'll be discussing today is complex, but from a remediation standpoint, the biggest by far that Maureen touched on is related to the contaminated groundwater matrix, fractured sandstone, and the associated back diffusion from the matrix. Back diffusion can occur with as little as an order of magnitude difference between hydraulic conductivities of adjacent matrices. Here we have a stand layer adjacent to clay. We'd expect significant difference in hydraulic conductivities between these materials. Effective contaminant transport, contaminant traveling with the bulk groundwater flow, is greater in the more transmissive zone. But affected groundwater also migrates into less transmissive zones here into clay by diffusion. This slide shows a remedial effort which cleaned the more transmissive zone. This changes the diffusion gradient and recontaminates the higher flow zone, causing a contaminant concentration rebound in the more transmissive zone. This back diffusion will occur for at least as long as the contaminant has been present, probably much longer. This flow chart shows the steps of managing any project, from grocery store shopping to complex remediation sites. And I know it's correct because I got it from Wikipedia. So the way it basically works is that after initiation, all projects go through a planning stage, a performance stage, and a testing phase. If the test is passed, then the project moves to closure. But if the test fails, then you basically need to start over. At complex sites, this can become a nearly endless cycle. The way to break the cycle is to inject actionable data early on into the project management cycle. Actionable data provides a more direct path to closure. So what is actionable data? Well, actionable data can come from any data collection activity that defines project direction. The illustration here is a great example of actionable data. The top image shows a typical nested well scenario to characterize and solve contaminant distribution. The data collected from the well is analyzed in an offsite laboratory and is highly accurate. The bottom image shows the same contamination scenario as above, but in this, a semi-quantitative logging tool is used to gather data. Not only is the estimate location of the plume significantly different, the dashed line at the bottom of the figure overlays the plume outline from the above to the bottom one. The total contaminant mass differs significantly also. It is easy to see how, in this case, the use of downhole logging could change the direction of a remedial approach at a site. At nearly every remediation site I'm involved with, we take a fail small, win big approach with actionable data collection. This typically involves collecting data to define treatment efficacy and mechanisms using site media performed at sub-full scale. In short, I bench tests, perform in situ microcosm studies, ISMs, or pilot tests for nearly every application. From a cost perspective, performing these studies makes a lot of sense. Typically, bench and ISM studies cost around $5,000, less often. And pilot tests are usually just a few percentage of the total full-scale remediation costs. This approach also has given me the freedom to test new technologies to take historically managed sites through cleanup to regulatory closure. For example, we recently decommissioned a pump and treat hydraulic containment system and replaced it with a continuous oxidant, REGENOX, dosing system, which operates at a fraction of the price of the pump and treat system. A bit about the fail small, win big testing. I typically use bench tests for in situ chemical oxidation and in situ chemical reduction projects. The primary use is to determine dose, efficacy, but the bench test also identifies undesirable intermediates, metals mobilization, and is a check on safety concerns like heat generation and off-gassing. Having a little trouble making the slide forward, if you bear with me for a minute. Here we go, I'll use that. Here's a quick example of a fail small bench test. The bench test was conducted using a protocol we've developed which uses near field scale soil to water ratios. We've found that this protocol provides results that can be scaled up to field application. The test involved assessing a presumptive ISCO activated persulfate remedy to treat chlorobenzenes. The top plot shows demand, persulfate consumed plotted on the y-axis, and persulfate dose plotted on the x-axis. The results are consistent with reaction kinetics over a fixed period of time. Higher concentrations of reactants means more reactions. In the middle plot, the dissolved concentration of total chlorobenzene is added. The red line, the blue line, that's the total concentration is the red line. The blue line is the demand line, and that hasn't changed from the plot above. You can see that the concentration trend is increasing. Not exactly what we were hoping for, but this isn't all that unexpected, as the treatment could have been caused by partitioning from the sorbed phase to the aqueous phase. This sometimes happens with ISCO. In the bottom plot, the green line is the total chlorobenzene's mass in the reactor vessel. It's soil plus groundwater. Apparently, there was some chlorobenzene's mass transfer between the sorbed and the aqueous phases, but there was no treatment. So here we feel small at a $3,000 price point. Getting back to the other fail small and hopefully succeed big testing. ISMs are open systems that are often deployed in monitoring wells. The image below is an ISM from Microbial Insights, which most of you are probably familiar with. I use ISMs for amendment bake-offs, confirming efficacy, and taking deep dives into degradation mechanisms. Here's a quick example of an ISM study. We performed this study at the same chlorobenzene site that we just discussed after the bench test failed small. But first, a bit of background. After the ISCO failed, we turned to bioremediation remedy. Bio for chlorobenzenes can get a bit complicated because it's easy to reduce tri- and dichlorobenzenes to chlorobenzene and benzene in anoxic environments. But treatment of these daughter products, especially chlorobenzene, are typically performed in aerobic environments. Well, we found this study. The study involves ISMs and a diagnostic tool called stable isotope probing, SIP. SIP traces the fate of isotopically labeled contaminant to microbial biomass, or dissolved inorganic carbon, the respiration byproduct of the biomass. The published study demonstrated complete degradation of chlorobenzene in anoxic conditions, presumably by anaerobic oxidation. These are the same conditions at our subject site, zero measurable DO and negative ORP. This was exciting because it meant that we could formulate a single amendment which reduced the more substituted chlorobenzenes and oxidized the chlorobenzene and benzene all anaerobically. Potentially a much more efficient scenario for the removal and treatment because it has one injection replacing two discrete treatments. So we basically repeated the study at our site, but we used 100% C13C labeled chlorobenzene so that we could provide a strong enough signal to trace the labeled DNA into the attenuating microbes. We did trace the label into the DNA. The DGG track on the right, that's this over here. Sequencing the bands of similar DNA showed that the predominant attenuating microbe was from the genus Acinetobacter. Acinetobacter is an obligate aerobe, definitively showing that the degradation pathway at this site was not anaerobic oxidation. Rather, it was aerobic. So in this environment where we had 0 DO measured from our field instruments and added nutrients that would drive the system more anaerobic, we were able to have degradation, aerobic oxidation under microaerophilic conditions. This actionable data dramatically changed the direction of the project. Here is a representative full-scale results performance monitoring. That was a pretty quick version of this ISM testing that we did at this site. We've published the study. If you'd like more details, please visit it and call me if you have any questions. Finally, pilot testing. Unlike bench tests and ISMs, pilot tests affords the opportunity to assess delivery characteristics. And there are lots of data options for efficacy and mechanistic data collection too. The balance of this webinar provides examples from the 2 large pilot tests that Maureen described briefly earlier. The site's in Arkansas. It's a former manufacturing site that began operation in the early 60s. Operations included use of chlorinated solvents. Contaminants included TCE and its daughters. TCA and its reductive daughters are also present, but at lower concentrations. Affected groundwater is present in fractured sandstone matrix, where back diffusion is a major concern. The sandstone fracture network have a predominantly horizontal fracture pattern with some high angle fractures also present. Veda zone source areas have been removed and vapor mitigation systems have been installed. This cross-section shows a site conceptual model. With the facility at the top of the hill, the pilot test area is a few hundred feet down gradient from the facility, and the plume discharging some VOCs to a stream located 1,000+ feet away from the facility. The Veda zone sources have been excavated and removed, and vapor mitigation systems have been installed under the overlying vapor mitigation system has been installed in the buildings overlying the plume. A little bit of a tangent here. One of the vapor mitigation systems was installed using a 300-foot long horizontal borehole. My colleague Steve Kretschmann designed the system. He also just designed and installed an amazingly efficient resin-based treatment system for 1,4-dioxane and chlorinated solvents at another site. So nice work by Steve. Back to the site characterization and the biggest confounding factor with respect to remediation, the saturated matrix, the fractured sandstone here. We expect long-term back diffusion, as we mentioned. With the challenge frames, an assessment of the remedial alternatives identified hydraulic containment and in situ remediation as potentially viable. To fully assess the best alternative to the site, a pre-design study was performed. We're actually in the middle of it right now. The pre-design study includes installing wells for pump and treat pilot test or pump test, and in situ and for use as injection points for in situ remediation pilot test. Collecting data, but the pre-design study also included collecting data about the nature of the sandstone fractures, fracture faces, and pump test to determine hydraulic characteristics of the fractured sandstone aquifer. I'm not going to get into the pump test results. That's information for another webinar. Performing a biogeochemical test was a major part of the pre-design study. 1 year of performance monitoring, which included conventional and advanced diagnostics, was included in the pilot test. To date, we have collected a baseline plus 3 quarterly rounds of data, 1 more remaining. So later on, as we got into this, we decided PlumeStop was a potential game changer for the site. So we performed a 4-month pilot test. We currently made the injection 2 months ago and collected the first round of data last month. All right, so this is a site map showing the plume distribution. The pilot tests were conducted in these adjacent areas. A couple of things to note here. For the 2016 pilot test, the Bio plus Biogeochemical pilot test, the amendments were injected through OW2. You'll be able to see it clearly in the next slide, or the next couple slides, not through IW1, which is intuitively what you would think. IW1 didn't have sufficient sustainable yield to perform the injections. The yield of the site was about probably less than a gallon a minute. The wells within each oval were included within the performance monitoring. This included near field wells and far field wells hundreds of feet away from the injection point. Let's get into the amendment selection a little. In situ treatment of chlorinated solvents in bedrock historically has proven to be challenging. The first thing we did was make a list of characteristics of an ideal amendment formulation. First, the amendment needs to be applicable for the contaminants at the site. Here, chlorinated ethanes and ethenes. Having both ethanes and ethenes can also be problematic. Some oxidants aren't efficient at treating both classes of chemicals. For bio, TCA is a known inhibitor of D-alkyloides, the microbe that is capable of completely dechlorinating innocuous end products. Dechlorinated the chlorinated solvents to innocuous end products. Other characteristics of an ideal amendment are that it be easy to deliver into the fraction network and it be long-lasting to manage the back diffusion. So we made a matrix to tease out the best amendment characteristics for the site. When we made the matrix, PlumeStop was relatively new. We knew of potential problems with other sorbent-based technologies, mainly agglomeration and deliverability. So we decided to, let's take a wait-and-see approach with PlumeStop. We ruled out oxidants quickly because of limited longevity and other reasons. One of my favorite technologies for treatment of chlorinated solvents and overburden is CVI plus a fermentable substrate. In fractured rock, the ROI would be limited and there would be a strong potential to clog the fractures and divert flow of groundwater potentially to uncontaminated areas, so we ruled it out. We looked into nanoscale CVI, but with the history of agglomeration and some regulatory hesitancy in the literature, we decided it wasn't quite enough to tip the scales towards using it at the site. We thought of discrete use of bioremediation or biogeochemical reduction was possible, but there are potentially many ways to interrupt these pathways as well. However, the combination of biostimulation and biogeochemical reduction mitigated many of these risks of using these technologies discretely. Before we get much further, I should explain what biogeochemical reduction and potential synergies with bio. The technology goes by different names, but whatever you call it, it has been around as an engineered technology for more than 10 years. The technology involves abiotic reduction by ferrous iron minerals, similar to ZVI. The list here includes most commonly referenced reactive minerals in literature. There are many others. The basis of the REGENESIS product CRS, as Colleen mentioned earlier, is to provide ferrous iron to stimulate formation of these minerals. The documents to the left are great resources if you want to find out more information. I should also mention that naturally occurring minerals these naturally occurring minerals are likely responsible for degradation at many sites. Routine investigations at chlorinated sites should include looking for these minerals. Magnetic susceptibility is a great low-cost way for doing so. At the Arkansas site, our goal was to make macaronite, ferrous sulfide. The three-step process for biogenic macaronite formation is shown here. Step one is the introduction of ferrous iron via products such as CRS, or if naturally occurring ferric iron concentrations are high enough, then ferrous iron can be provided by reduction. This involves stimulating iron-respiring microbes such as Geobacter. Step two is the reduction of naturally occurring or introduced sulfate by sulfate-reducing microbes. Finally, step three is the rapid coordination of sulfide and ferrous iron to form a precipitate, iron sulfide. The step three process basically stores electrons from the fermentable electron donor within the ferrous sulfide minerals for later use. Note that the addition of sulfate to form ferrous sulfide to treat chlorinated solvents and some metals is a patented process. We work with Jim Studer of Infrassure to obtain a site license for some unique diagnostic capabilities that Infrassure has developed. Jim's contact info is listed here. Here are some iron and bio synergies that I mentioned earlier are listed. First, competitive inhibition between iron reduction and chlorinated VOC reduction, competing electron acceptors, has been disproving, at least where fermentable substrate concentrations are kept at reasonable concentrations. Iron improves conditions for DHC by reducing concentrations of known inhibitors, sulfide and TCA. Iron reducers also provide the vitamin B12, a necessary complement for halorespiration. DHC cannot provide B12 on its own. Some reduced minerals are not very reactive with dichloroethane. Biodegradation can manage those. So you can see that these work synergistically. There are other synergies listed here. Additional information on these and other synergies can be found in the Combined Remedies article, Thinking Outside the Boxcar, which we published earlier this year. End result of bio plus biogeochemical remedy is that 2 degradation pathways are stimulated. This slide is from a presentation I co-authored with Dora Taggart of Microbial Insights. It shows TCE biotic and abiotic degradation pathways. The biotic is straightforward sequential dechlorination. I'm sure you've seen it thousands of times. The abiotic pathway does not go through sequential degradation. A key differentiator between the biotic and abiotic pathways is product recovery. There's poor product recovery for the abiotic process. This slide shows degradation pathways for TCA. Again, the abiotic pathway has low product recovery. We can use the product recovery differences between the pathways to try and tease out the degradation mechanisms using F-abiotic equation. Basically, there is a good product recovery, abiotic process. The molar concentrations of parents, daughters and end products, ethane and ethene, will not change much, and the numerator will be a small number. A small number over a bigger number, or an F-abiotic term approaching 0. So that's the bio end approaching 0. Conversely, if the abiotic processes are responsible for the degradation, then the F-abiotic term will approach 1. There are some flaws with this equation, but for most of the time, it's not a bad way to tease out the mechanism. Here's a plot of performance monitoring data over a 3+ year period from another combined bio plus biogeochemical treated bedrock site. The pilot shows, in orange, average total molecular VOC data. And this was averaged over 8 different samples and normalized the baseline concentrations. The F-abiotic calculation results are presented in blue. The VOC data shows strong decreasing concentration trend, over 80% overall. The initial abiotic results show the term was close to 0, indicating biodegradation was responsible for initial concentration decreases. But the abiotic pathway becomes more important as the treatment progresses. This trend makes sense. Microbes use the fermentable donor in the amendment formulation to drive halorespiration. As the fermentable donor was consumed, the electrons stored in the ferrous sulfide extended the treatment by abiotic reduction. Let's get back to the Arkansas pilot tests. This picture shows the 2 pilot test areas. They're side by side. And this figure, here we have a closer look at the biogeochemical pilot test area. We installed 5 bedrock wells for the pilot test and completed geophysical logging, including natural gamma, televiewer, and 3-arm calipers. These data provided great detail on the location, size, and orientation of the fractures. We also collected core samples for a very detailed analysis by Infrasure. The level of detail in the evaluation was phenomenal. It would take an entire presentation to go through it. While we are looking at this slide, I also want to point out again that the injections were made through OW2, not IW1. So that's OW2 right here, not IW1 up here. Also, there's no scale in this image. So MW7 is located about 80 feet, MW7 is right here, it's located about 80 feet from OW2, and MW13 right here is located about 300 feet from OW2. The amendment formulation was specifically designed for the site based on groundwater chemistry and results from the Infrasure core evaluation. We assumed an 80-foot radius of influence and calculated that an amendment volume of 5,000 gallons was needed to achieve this ROI. The amendment formulation consisted of sulfate, CRS for ferrous iron, HRC primer, 3-DME were added for fermentable carbon. The CRS also provided some fermentable carbon. Bicarbonate was used to buffer pH, micronutrients were added, and the microbial augment BDI plus was applied. We also added 2 traces to OW2. Eosine was added before the amendment application and fluorescein was added after the injections. There were no issues during injections. For performance monitoring, we planned 4 rounds of sampling for the parameters listed here. This parameter list was designed not only to monitor VOC trends, but to assess the mechanisms of degradation. Here we see the results of the dye tracer testing. The dyes show great fraction network connectivity. The dye delivered to the most distant point pilot test well, MW13, 320 feet down gradient. Concentrations weren't all that high, but we showed connectivity. The footprint of the expected geochemical changes in response to the amendment was consistent with the dye tracer footprint. The heat map here, green, shows strong geochemical shifts. Yellow moderate, and neutral was white, and red was kind of negative. For example, pH in the top row. Green indicates pH increase from baseline of 5 or so to neutral, 6 or 8. Similar color coding was applied to each of the parameters listed. You can see the desired geochemical shifts were strong in IW1, located 30 feet up gradient of the injection well, all the way to MW7, located 80 feet down gradient of the injection well. Even MW13, 320 feet down gradient, showed some favorable geochemical shifts. This is a plot of the VOC concentrations within the pilot test area with time. You can see that we've completed 3 of the planned 4 rounds of performance monitoring events. The 3 highlighted trends for the injection well, the 2 up gradient / slide gradient wells, and it did not show much geochemical response. The wells highlighted in red on the Plume map in the upper right. If we eliminate these, it cleans up the plot a bit. We see decreasing VOC concentrations in all the wells, and very strong decreases from 30 feet up gradient of the injection point to 80 feet down gradient of the injection point, more than 100-foot long treatment zone. On this figure, total VOC concentration trends are plotted discretely for each well. The individual data point pie charts show the VOC mole fractions for each VOC for each sample. The legend defines the colors in VOC relationship. Red is for TCE, yellow is DCE, green is vinyl chloride, and blue for ethane plus ethene. In OW1, there is a great total VOC concentration decrease, but not many daughter products are present. IW1 and MW7 show great concentration decreases and sequential product degradation, reductive. IW2 shows a strong biosignature with lots of ethane and ethene. MW13 only shows a slight decrease in concentration trend, but does show some daughter product formation. Here we have added a plot of abiotic in the blue at the bottom. As you expect with OW1 data, the plot is close to 1, meaning abiotic processes dominate. IW1 and IW13 data close cut to 0, a biotic signal. In MW7 is a mixed bag. In this slide, CSIA data is plotted. Note that round 3 performance data is not included. The results are not in yet. The CSIA data gets a bit tricky to interpret than usual because back diffusion can mask isotopic enrichment. Nevertheless, there is isotopic enrichment of TCE in MW7 and in MW13, and DCE in IW1 and MW7. Finally, here's the qPCR data. It shows viable abundances of DHC, those abundances greater than 10 to the 4th cells per milliliter during at least 1 performance monitoring round test. Most of the wells for all of the performance monitoring round tests. all the wells with degradation trends had viable concentrations of D. helicoides. In summary, we achieved good delivery across a minimum length of 100 feet. The amendment formulation produced the desired effects, and we had great VOC concentration reductions. Both abiotic and biotic mechanisms contributed to those degradations. With the time remaining, I'd like to present the preliminary results from the PlumeStop pilot. We injected the PlumeStop in April, and the May performance monitoring results are very encouraging. Here's the site map to orient ourselves. The PlumeStop pilot was completed adjacent to the biogeochemical pilot, right here. Injections were made through IW2, up here, and monitored through MW6, OW6, and OW7. MW14 was also used for, as a monitoring well, but it's outside the field of the magnifying glass. It's located about 500 feet downgradient of IW2. For the amendment design, we assumed the same aquifer characteristics as the biogeochemical pilot. 5,000 gallons of amendment fluids were added. The amendment was comprised of PlumeStop. PlumeStop is an activated carbon source, as Maureen mentioned, is a sorbent matrix. It is sterically stable in groundwater. The sorbent characteristics basically attract the contaminant, the biostimulants, and the bioaugment all into one spot for efficient treatment. I look at this technology and these characteristics as being transformational to in situ remediation. The base technology, sterically stabilized activated carbon, is deliverable and customizable to treat many pollutants via many degradation pathways. I'm looking forward to see how the customization capabilities of PlumeStop evolve. The performance monitoring program for the groundwater samples is very similar to the biogeochemical pilot test. The major difference is that we crushed sandstone core samples and that we collected from the previous investigations, verified that there were no VOCs remaining in those crushed sandstone samples, and filled ISMs, which was basically a 1-inch well screen segment with this sand. We deployed 3 ISMs into each of the performance monitoring wells before the application of the amendments. The solid phase of these ISMs were subjected to the test listed under the crushed sandstone core in situ microcosms. So we were completing these on the Sorbed phase. Here are some photos of the ISMs. Like I mentioned, we crushed the sandstone with a hammer and collected the sand that passed through a 35 mesh sieve but was retained by a 5 mesh sieve. The crushed sandstone was then deployed into 1-inch diameter well screens and deployed into the monitoring wells. The goal of the ISM samplers is to quantify degradation on the PlumeStop particle, it's a sorbent, and hopefully get an idea of the rate of degradation to compare to the rate of back diffusion. If the rate of degradation is greater than the rate of back diffusion, the treatment will be sustainable as long as favorable biodegradation conditions are maintained. The first bit of data we collected as part of the pilot test was the change in groundwater elevation head in the monitoring wells during injection activities. These data show strong connectivity and are very encouraging. Basically, for a full-scale application in this matrix, we should be able to tweak the amendment volume and concentration to manipulate the radius of influence. In the near field wells, those 35 and 50 feet away, we had greater than 10 feet of head change during injections. And in the far field wells, we even had change. At 140 feet away, we had about 8 feet. And at cross gradient to that 140-foot well, it's about 165 feet. We still had 4-foot head change. And this was all done under low pressures, probably about 30 psi at the injection head. The field parameters provide additional information on radius of influence. There was a strong influence at least 50 feet down gradient of the injection point, which is indicated by these green highlighted cells. There was even some influence at the 140-foot monitoring wells. Here it is, the VOC data. After only 1 month, probably before everything even settles down, we have an 80% total VOC concentration decrease 50 feet from the injection point. That's pretty phenomenal. Here is a mole fraction figure for the samples collected from these wells. This is all in the aqueous phase. The injection point in nearby downgradient wells showed dotted product degradation. So dotted products and degradation. qPCR data collected from the ISMs, so this is from the soil phase, so measuring it from the PlumeStop itself, is consistent with the mole fraction shifts towards dotted products. The abundance of DHC is high in the nearby wells and non-detect with a high detection limit in the more distant wells. The injection well didn't have an ISM installed, so the DHC abundance in the aqueous phase was about 300 cells per milliliter. It was a bit low. Again, this is only 1 month following application. Figures. So this cell, my notes disappeared, so I'll try to explain it on the fly, shows the concentrations in the ISMs, and so the Sorbed phase versus, and that's in brown, versus the predicted VOCs that would be in that sample if all the VOCs were contributed from the soil moisture. So we basically multiplied the ISM percent moisture by the groundwater VOC concentrations. So starting at the most distant downgradient area where we should not have PlumeStop delivery, you can see that these lines are fairly close, that the concentrations that are in the soil measured in the PlumeStop particles is about equal to, there was no, in the soil Sorbed phase, the crushed sandstone is about equal to the concentration predicted by the soil moisture. Closer to the source area, we can see that the concentration in the Sorbed phase is much, much higher than that would be predicted if the VOCs were only attributable to soil moisture. Effectively, the PlumeStop increased the KD of these surrounding soil, of the sand matrix and the fracture faces for which it flowed. All right, so here's the conclusions for the pilot test. This is probably the quickest slide that we've had. It's early on, so it's very encouraging. Before we get to questions, here's the highlights of what we've learned from these pilot tests. The fracture network provides for a large delivery radius of influence. We've stimulated desired geochemical and microbial conditions. We've achieved 80% contaminant reduction in both pilot tests using amendments that have plenty of active life remaining. And we have supporting degradation pathway data for the biogeochemical pilot test and are very optimistic about the PlumeStop pilot test. Not only are we highly optimistic that we'll be able to remediate the site with an in situ remedy, but we're excited that we'll be able to do it in a sustainable manner. Here's the spreadsheet results for the environmental footprint analysis using EPA spreadsheet for environmental footprint analysis, or SEFA. We compare the footprint of a pump and treat system to that of an in situ remedy. The pump and treat input parameters included 20 pumping wells, air sparging, activated carbon polishing, and O&M for 20 years. For the in situ remedy, the input parameters included 20 injection wells, amendments, and 5 injection events over 20 years. The results show in situ treatment to have a much smaller environmental footprint. For most parameters, 1 to 2 orders less than that of the pump and treat scenario. Finally, I want to thank our client, REGENESIS, and the project team. I think we have a few minutes left for a few questions.
Okay, thank you, Matt. That concludes the formal section of our presentation here. Just a few reminders. First, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, after the webinar, you'll receive a link to the recording as soon as it is available. All right. It looks like we have maybe a few minutes left for questions. I'm going to give a second or two for folks to get their questions in. If they'd like, you can pose a question to Matt or Maureen. Also, I'll note here that if you would like more information about engineering solutions from WSP, you can go ahead and visit WSP.com. And also, if you need immediate assistance with a remediation solution from REGENESIS, you can visit regenesis.com to find your local technical representative, and they'll be happy to speak with you. So we are...
Dane, I have one other thing I'd like to point out.
Sure.
One of the versatilities of PlumeStop is that you can actively park it to keep it from flowing outside of areas that you want it to be distributed to. We did that at this site using calcium. So it's another great characteristic of the PlumeStop is that you can stop the amendment from traveling before it hits an area you don't want it to hit.
Okay, all right, yeah, thank you for adding that. All right, so we are starting to get some questions pouring in here. Here's a question, and the question is, how do you control for potential clogging from microbial biofilms?
I have never had that problem, but the one way to control that is through your dose of electron donor. So I always try to stay as close to stoichiometric as I can while retaining some long-term release capability. So the best way is to not feed them too much.
Okay. All right, great. Thank you. Let's see here. The next question is, what was the fracture pattern and how was that considered in both the contaminant distribution and product injection?
So the majority of the fracture patterns were horizontal, but there were some high angle fractures connecting those. We used the TeleView or data logs to estimate the void size of those fractures and calculate a mobile porosity. And then we targeted a % replacement of that mobile porosity for the amendment volume.
All right. Okay, thank you, Matt. Let's see here. The next question we have is, how do you get the sorbed contaminant out of the aquifer once PlumeStop has been injected?
Well, the whole goal is to have the degradation occur on the PlumeStop, and that's why we have those in situ microcosms placed within the monitoring wells. So we place those before the PlumeStop injections, and the PlumeStop distributed itself throughout the fracture network, onto the fracture faces, and also onto those crushed sandstone in situ microcosms. So we'll be collecting data from those in situ microcosms periodically. We deployed 3 in situ microcosms per well, so we'll be able to collect 3 rounds of data, and that's going to include VOC analysis and isotopic analysis. The VOC analysis is in, and we see that there's degradation occurring, and we actually have some preliminary ethene data and ethane data that shows there is complete degradation going on. The isotopic data is probably going to be the most important data, so we'll be able to definitively show if degradation is occurring by observing fractionation.
All right.
So the whole goal is to keep the PlumeStop clean by having bioactivity to remove the VOCs. That way it creates room for the VOCs that are back diffusing from the matrix to sorb to the activated carbon PlumeStop particle.
Okay, all right, thanks, Matt. Let's see here. Yeah, we got some more questions pouring in, so we'll just keep going. We have about 5 minutes left here. So The next question is, were permits required for your injections?
Yes, and my wonderful project team handled every little bit of that.
Okay. All right, good to know.
We had no issues. That's probably another thing to point out. It was routine. We didn't have any regulatory pushback.
Okay. All right, great. So next question here is, if activated carbon has dispersive polymer, won't it continue migrating down gradient, advective flow, going out of the treatment zone?
So this is my preemptive answer. So you can break that polymer. It's an anionic polymer, so if you add cations, it will knock it out of solution. So we added calcium at this site to prevent it from traveling too far. So, and that can be precisely placed. I could have placed those at a down gradient monitoring point or down gradient point to stop the PlumeStop from going beyond that barrier. At this site, we injected it soon after the and a little bit with the PlumeStop itself through the single injection point.
Okay. All right, great. Thank you. Let's see here. Next question is, has this been tested in fractured igneous or metamorphic bedrock?
So, Maureen will take this, but my quick answer before Maureen gets on is that it should be easier because you should have a lot less back diffusion from those matrices. Maureen?
Yeah, I know there are other formations that we've, other bedrock formations that we've applied PlumeStop in and have had some good success, but I can get back to the person asking the question with some specifics on the type of, the specific bedrock formation that we've used, but we've had about 4 or 5 other applications.
Okay, great. Thanks, Maureen.
Dana, do you see the image that's up there right now? This is the PlumeStop ISMs pre-deployment. You can see that they're nice and white. Post-deployment, close to the well, you can see that they're coated with the PlumeStop, so the PlumeStop has fallen out of solution and stuck to the surfaces near it. And this is the 140 foot. You can see that there's a little bit of PlumeStop there, but we effectively manage the PlumeStop distribution by adding that calcium.
Okay, great. No, that's helpful. Thanks for pointing that out. Let's see here. So next question is, did you conduct design verification borings to confirm your 80-foot ROI?
So no, we just used the monitoring network that was shown on the figure.
Okay. All right, so looks like we have a couple more minutes here, maybe time for 1 or 2 more. Yeah. Looking at the next question here is, how do you know the contaminants are degraded versus adsorbed and sequestered by liquid activated carbon?
Well, that's part of the study, and we do so through the question I answered a few questions ago. We hope to get that data from the in situ microcosms that were deployed during the pilot test. So we'll look for isotopic degradation or isotopic fractionation to prove definitively that there's degradation going on. That data isn't in yet, but we do see sequential reduction to data products through hydrogenolysis. We also have ethene generation. So we don't have the units yet, but we know it was generated. So we definitively know we have ethene in those in situ microcosms. So that's the complete degradation pathway. So we tried to go out there and stimulate hydrogenolysis, sequential reductive dechlorination. We see data products and we see ethene. So we know that we're having mineralization. The CSIA data will provide additional information to that end.
Okay, all right, thank you, Matt. So maybe one more question here, and that is the abiotic TCE process ORP dependent?
That's a trick question. So for many, in order to have these minerals survive, they need to be in anoxic waters. But some, like magnetite, can survive in aerobic waters. So you can have magnetite degrading PCE, TCE in the presence of aerobic conditions. Now, I don't know how I would possibly try to engineer that, but that's more applicable to natural situations where you see decreasing concentration trends of TCE or PCE, but you don't see any data products, but you plugged it into a model that generated a rate and you don't know where it's coming from. It's probably from co-metabolic activities or through this abiotic degradation with magnetite.
Okay. All right, well, thanks, Matt. That will be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. As I said before, if you would like more information about engineering solutions from WSP, please visit WSP.com. If you would like assistance with a remediation solution from REGENESIS, please visit regenesis.com to find your local technical representative, and they will be happy to speak with you. And thanks again to Matt Burns and Maureen Dooley. And thanks to everyone who could join us. Have a great day.